Okay, let's do a small problem to elaborate on the idea of the energy release rate. So the problem is how much energy is required to form a Griffith crack. If you remember, a Griffith crack was this problem, infinite plate with a crack of length 2a at the origin, centered at the origin. This is x2, this is x1. And this is subjected to remote tractions S according to the problem. We had not solved this problem explicitly, but we had shown that this is similar to the problem of an infinite plate with no remote load, but with uh, the same crack subjected to crack face tractions of magnitude S. This is x1, this is x2. It's the same crack. And these two problems are equivalent, we have shown in the last, in the class before the break. And for this problem, we had derived the crack opening displacement. So I'm exaggerating the crack here. This is your x1, this is your x2. So for this crack, for this problem, we have derived u2 as a function of x1. This is the crack opening displacement. And since these two problems are equivalent, the crack opening displacement for this problem will also be the same. So this is the displacement. This is the crack opening displacement as a function of x1. Now, this crack, this opened crack, which now has traction-free surfaces, started off as, so if I draw a line where the crack is going to form, so this line is of length 2a, in the uncracked body, so this is x1, this is x2. So in the uncracked body, this is not a crack, this is just the line denoting where the crack is going to form. So in that situation, when there's no crack, everywhere the stress is equal to S. So sigma 22 is equal to S and every other stress component is 0. The stress state is given by sigma 22 equal to S and sigma, all other sigma ij equal to 0. So on this face as well, on this line as well, the stress state was similar. So the stress state was sigma 22 equal to S and every other stress equal to 0, but the displacements, there was no crack, so there was no crack opening displacement. So the crack opening displacements were 0, whereas let's call this state 0, and this is state 1, where we now have two surfaces which have no traction. So the tractions, so the stresses have gone down, tractions have gone down from S to 0, and but there is a displacement u2 that has now come in. So the question is, what is the change in the potential energy from state 0 to state 1? Given that we know that in state 1, this is the displacement, this is the crack opening displacement that you can expect. So kappa, of course, is different values for plane strain and plane stress. So to calculate this, so this process is elastic, completely elastic. There's no plasticity involved. So let us draw the crack. So let us draw only the upper part of the crack. The lower part is symmetric. It's a mode 1 problem. So this is x1, x2, and let's take a small segment dx1 on the surface of the crack. Now let us figure out what is the energy required to close this upper part of the crack, and this being an elastic and therefore reversible process, the energy required to open the crack should be equal to the energy required to close it. So what I think about this is, in order to close this crack, you now have to apply a traction. This is a traction-free surface. You have to apply a traction and pull it down. So what you are doing is, if I plot the traction on this, um, let's plot the traction here on this small segment and the displacement of this small segment. So uh, at the beginning, the traction is equal to 0, but the displacement opening is equal to u2x1. So this is u2x1 for this. And then when you have closed the crack, then the traction goes up to minus s times dx1 into the thickness. So s is, remember the normal at this is 0 minus 1. So the traction is equal to minus sigma 22. When you close the crack, it is equal to minus s times t dx1 is the total force. So this is not the traction, this is the total force that I'm plotting, total force on this. So at that point, u2 will be 0, and this will be the traction that will apply on the crack once it is on this upper crack face, once it is closed. So at this stage, the traction at this point would be equal to, or df at this point would be equal to minus s t dx1, s being equal to sigma 22, s being equal to sigma 22 when the crack is completely closed. So by some means, in state 1, it is at a state of 0 force applied on the crack and some displacement. In state 0, it is in this state, it is, and in the closed state, it has no displacement, but it has a force of minus st dx1, t being the thickness out of plane. And being a linear process, it will, we can assume that the path is linear. We can actually assume any path. So this is the closing of the crack. You go from displacement but no force at this state to this traction but no displacement in the closed state, and this area is half st dx1 times u2x1. So this integrated over 0 to a gives you the total energy required to close this whole part of the crack to a slit like this, and multiplying by 2 gives you the energy required to close the total length 2a of the crack. So this is what you need to calculate, and this is easy to calculate if you know u2x1, which we do, and if you carry out the integral from 0 to a, then this is the answer that you will get. So this is the idea. This is an example of how we use Griffith's idea in order to figure out how much energy must have been released when the crack is formed. Crack of length 2a is formed. Now this when a crack is formed, energy is released, but we figured out that energy by closing the crack. When we close the crack, we have to pump in energy into the system. So the signs are different. The signs will be different, but the magnitude of the energy that is required to close the crack and to open it should be the same, provided everything remains elastic. As we have discussed in energy methods in fracture, the key quantity that we need to determine is Gc, which is the critical energy release rate. It is the critical energy release rate, and remember that for crack to grow, G should be greater than equal to Gc. This relation is exactly like K1 greater than equal to K1C for crack growth, whereas where K1 is a quantity that we arrived at, is a driving quantity for the crack, it's a stress intensity factor that we arrived at by looking at the local crack tip fields. Okay, so the local crack tip fields are characterized by the single parameter K1, and we said that since there's only one parameter, then the critical value of, there should be a critical value of the parameter beyond which the crack starts propagating catastrophically. Whereas in this case, in energy methods, we say the driving factor is G, which is del U by del A, and this driving quantity which I apply on the crack is should be greater than equal to this critical quantity, which is a material property for the crack to grow catastrophically. See here that we have arrived at this statement from a global perspective. Why do I say that? I say that because we arrived at this by summing the energy from basically an energy balance, a bookkeeping of the energy, by saying that the total potential integrated over the whole body should decrease when the crack forms. So that's the basic idea that we used. It's a global statement. So this G and GC are sort of global quantities. We have arrived them at by integrating things over the whole body and not from the local crack tip field like we did in the case of K1. We will later show in a couple of class lectures, we will show that G and K are indeed related to each other, and they basically tell you the same thing, but then GC turns out to be somewhat easier to determine experimentally than K1C. Also remember that the units of GC and K1C are not the same. Units of G and K1 are not the same. K1 has units of MPa root meter, whereas G and GC are energy per unit area. So it is Newton meter divided by meter square, that is Newton per meter. So G has units of Newton per meter, whereas K has units of MPa root meter, but we will later show that these two are equivalent quantities. But before that, let us look at a thought experiment by which GC can be determined. GC can be determined. So let me erase this. Now, here at state 0, we have a body testing sample which has a crack, and it is connected to a machine through which a load P and displacement, load point displacement delta, these are measurable quantities. These are measured with force gauges and displacement gauges maybe. And the machine itself is a stiff machine, but its stiffness is given by Km. So when you apply this force, there's a possibility that the machine itself deforms a bit. So its stiffness is given by Km, which is a constant for the machine, and the machine is the specimen is attached to the machine, and the specimen stiffness is given by Ks, which is a function of A. Now, between state 0 and state 1, the crack has grown by a small amount delta A. So the stiffness of the specimen has changed from Ks A to Ks A plus delta A. So the stiffness of the machine has changed. The stiffness of the specimen has changed. The stiffness of the machine, of course, remains constant, and the load and displacement are P and delta. Now, obviously, the total delta is delta of the specimen, the load point displacement here of the specimen, and the load point displacement of the machine, which is the force is the same. The force is the same force transmitted. These are two springs in. So we have actually replaced this cracked specimen by a spring of stiffness dependent on the crack length. So P by Ks is the displacement of the specimen, P by Km that of the spring. So P is given as a function of delta by this equivalent stiffness condition, and the strain energy density U is half P times delta, which will now be given by this. So this is the total strain energy stored in this system at state 0. Okay, now this undergoes a small change in A, so we will figure out what is the del A of this quantity. Okay, so we will actually find out not del A but del capital A, which is equal to del U del A times T, where T is the out of plane thickness of the specimen. So this is the P. So we are trying to figure out del U del A equal to del U 1 by T del U del A, and U, remember, is delta square times this, and based on Griffith's idea, del U del A plus Gc has to be less than equal to 0. So and when I do del A, this is not a function of A, this is only a function of A. So when I do the derivative, I have to take a derivative of Ks del A, and this is what I get. This is what I get. Okay. So this is the condition that I get from Griffith's theory. The total strain energy, which is half P delta, can also be expressed in a slightly different way. We had already written it. So we are just rearranging this equation by taking the Ks out. So it can be rewritten in this fashion, and you can clearly see that now this quantity here, this quantity along with one of the Ks is equal to Us. So this can be written as minus Us by Tks into dKs dA is greater than equal to Gc. So this is the equation for crack growth, equation at which the crack will grow. So if I can figure out, so I keep on increasing this P, that means I keep on increasing the strain energy that I'm pumping into the system. At some point of time, this condition will be satisfied. If I know the P and the delta at that point, when the crack, this crack just starts to move, so that I go from state 0 to state 1. So I have to locate that point. At that point, I will take the P and delta. If I take the P and delta, I can calculate the US at that point. And then if I can figure out the rate of change of the stiffness of the specimen, then I can use that to determine Gc, because at that point where the crack just starts to grow, the left hand side and the right hand side are going to be equal. So this is going to be equal to Gc, and to do that, I will have to figure out what is the rate of change of the stiffness of the specimen with respect to crack length. To do that, what I can do is I can do experiments with multiple specimens. So what I can do is I can take several specimens with different crack lengths A, and do this experiment for all of them. And then this can all be sorted out graphically, as I will show now. Now imagine that we are doing a test with the same specimen that I showed in the previous slide. And I have several of them with different crack lengths A. Consider 2 where A2 is greater than A1. So I have two specimens, one with a longer crack and one with a shorter crack. Now I can do different kinds of experiments. So I can apply the P delta. Right now I am assuming that the machine stiffness is, I'm neglecting the idea about the machine stiffness. So I'm applying this P or delta, and I can do two kinds of tests. One is I can keep the P to be constant at P star and increase delta. In the other case, I can keep delta fixed and increase P. So let's first look at the fixed load test where I keep P is equal to P star. I keep P is equal to P star. Now, since this is a linear elastic problem, for any crack length, when I increase delta, P will also increase linearly. So for the shorter crack length, it will have a higher stiffness. The shorter crack length specimen will have a higher stiffness, and let's say this is its P delta curve. Okay, and for the longer crack, this is the P delta curve. Both are linear. Both are linear. This is the P delta curve. Now I am actually holding P at P star. So I am actually always holding the load here, and I see that for the specimen with the shorter crack length, the crack just starts to propagate at this point where the displacement is delta 1, and for the longer crack, the crack just starts to propagate at this point where delta is equal to delta 2. Okay, and let us assume that A2 and A1 are not very different. They are close to each other. So the change in strain energy, the strain energy at crack initiation for the shorter crack is this area, half P delta. The strain energy for the longer crack is this area. The potential of the loads is this area. This area, right? And if you do the so these two areas have to be added and this has to be subtracted. So if you do that, you will see that you will be left with this area OAB. You will be left with this area OAB. So this OAB gives you the change delta pi that occurs between crack lengths A1 and A2. And if you divide this, if A1 and A2 are not very different, then you can divide this delta pi by delta A1, that is A2 minus A1. You can divide it by A2 minus A1, again divided by the thickness of the out of plane thickness of the specimen to get the crack area, and that will give you the energy release rate. That will give you the energy release rate in this experiment. So we can do this at constant fixed grips as well, where delta is fixed. So again, this is the load displacement behavior for A1, the shorter crack. This is the load displacement behavior for the longer crack. Now I'm holding delta star to be fixed grip loading, and load and crack extension occurs at this load and this load. Since I am holding delta star fixed, there's no external, there's no potential of external loads. So the change in potential energy is equal to change in strain energy, and strain energy for the shorter crack is this area, and for the longer crack is this area, and the change in potential energy between these two is again this intervening area for a fixed grip case. And as I said, you can divide this area OAB by T times delta A to get the GC from experiments. Let us do a problem which will make it clear. So this is what is known as a SCNT specimen, single edge notch tension specimen. So that's a specimen that I drew in the previous slide. So this is an edge notch. is fixed is held here, and a load P is applied and delta is specified. So I have several P delta readings from several crack lengths. I have 1, 2, 3, 4, 5, 6 samples, 6 samples with different crack lengths, which initiation of the crack, when the crack just starts to move, I note down the P and the delta from the machine. Okay, and this table gives me the results of an experiment at which I have noted down the P and delta for each of these cases. And as you can see, as the crack length increases, the P starts to drop and delta starts to rise, so that you get more displacement at crack initiation, whereas less load is required to initiate the crack. So this is neither a fixed load nor a fixed grip experiment. So what I'm going to do is I'm just going to take two consecutive values, let's say this and this. I'm going to call it the ith and the I plus 1th, and what I'm going to do is between these two I am going to plot the P delta responses. So this is for the shorter crack, this is for the longer crack, and then what I am looking at is this yellow area. This is the change in the potential energy that takes place for a crack of length AI plus 1, AI going to AI plus 1. I am doing this experiment separately, but I am assuming that when the crack goes from length AI to AI plus 1 in a continuous experiment, the situation will be the same. So the energy required will be the same. Okay, so to find this area, again we go by the same route. We first take this triangle, which is, I guess, this. Then we take the area of this trapezium, which is this, and then finally we subtract the area of this triangle, which is this, and this leads to this. You can work it out, and this is how these are quantities that I know: pi delta I plus 1, pi plus 1 delta I have noted down from the experiments. So I just plug in the values, and then Gc would be the yellow area divided by T times the change in crack length. And if I do this, I should be able to derive derive Gc and then I can expand this table. I have calculated the Gc here, and as you can see, the Gc remains roughly constant. You can take average of this to get the Gc of the material. Now we have seen that when the crack just starts to grow, the rate of change of potential energy of the system with increase in crack area is equal to minus Gc. So this condition is satisfied at the point of crack growth. Now let us define the energy required to form the crack, so that d gamma, this gamma is the energy required to form the crack, is Gc times dA, in which case this equation can be written as ddA of G plus gamma equal to 0. So this is the condition. So G plus gamma, which are both functions of the crack area, is either a maximum or a minimum at the point of crack growth. And now we can obviously look at three situations when this is less than 0, when the second derivative of pi plus gamma with respect to A is less than 0, we have unstable fracture. When it's greater than 0, we have stable fracture. When it's equal to 0, we have neutral, a neutral situation, just like any other problem involving maxima and minima. So let us look at it. So this is so here's a problem where we are peeling off a layer of mica. This is a big block of mica from which mica comes in sheets, and we are peeling off a layer by pushing a wedge, a square wedge, through in this direction. We are pushing the wedge, and at this point the peeled length is equal to A, and the height of this block is H, so this opening is equal to H. Okay, and the thickness of this is D. So the elastic, to find the elastic energy, strain energy stored in this beam, which is actually a mica with thickness D, we have to treat this as a cantilever which is built in at this point. So it has a length of A and a displacement of H. So we know that the force, assuming that there's no friction at this point, so the force is equal to P. So we know that H is equal to P A cube by 3 EI. I for this case is D 1/12 T is the thickness and D cube is the height. So this is equal to I. Substitute this here and then you get a relationship between H and P, and from there the total strain energy in the body is half pH. That can be determined as ET d cube H square by A cube. Now the energy required to peel the mica is given in terms of gamma plus unit area. So the total energy required, gamma is the energy required to peel unit area of mica. So the total energy is 2A times gamma into T, 2A being the two surfaces that you need to create in order to peel, in order to extend the crack. So this crack, the crack here is being extended and the total, to extend this crack, del A of U plus gamma has to be equal to 0. So instead of doing that, what we are going to do is we are going to plot it as a function of the crack length. So we can also plot it as a function of T times A. T is a constant, so we can plot it as a function of crack area also. So this is how U behaves. This is how U behaves. So it is a decreasing function of, as A increases, U decreases rapidly. Whereas this is an increasing function of A. As A increases, it increases linearly with A. So this is the behavior of gamma, this is the behavior of U, and this is the behavior of U plus gamma, which is the sum of these two. And as you can see, it is equal to 0 here. Del A of U plus gamma is equal to 0 here. And to find the value at which it is 0, you have to take its derivative. You have to take its derivative with respect to TdA, and that will give you the critical crack length, critical length of the crack at which the growth condition, which is this, the growth condition which is satisfied. So when the growth condition is, after the growth condition is satisfied, what you can see, to make the crack grow further, you have to actually increase the energy. You actually have to increase the energy, which means that this is a stable crack. That means a small increase in energy will lead to a further small growth in the crack. So this is a stable case, which you can also see by taking the second derivative of U plus gamma, which is positive because every quantity in this expression is positive. So you have a positive value of the second derivative, which again tells you that it's a stable crack. Okay.